Hello everyone, this is Dr. Webb and welcome to this abstract algebra video. In this video we are going to be continuing our look at polynomial rings, particularly polynomial rings over fields, and we're going to be proving unique factorization in these polynomial rings. You're aware in the integers how we're able to factor any positive integer into a product of primes. Well, very similar situation takes place in these polynomial rings. And so we will show and talk about to what extent that is true. So first we're just going to review over some definitions and things that we've proven over the last couple of videos. So one thing that we've been talking a lot about lately are principal ideal domains. And so these are integral domains where every ideal is principal. So for any ideal, you can find some element in the ring such that that ideal is just generated by that one element. And one of the things we proved in the last video is that if f is a field, then the polynomials over f is a principal ideal domain. And so that means that every ideal of these in this polynomial ring is generated by a single polynomial. So we're also going to be talking a lot about prime ideals and maximal ideals. So let's review over those definitions. So in a prime ideal is when if you have a product of two elements are in the ideal, then it must have been that one of the two elements was already in the ideal to begin with. And then for a maximal ideal, an ideal is maximal if any time that you have, if I is maximal, if any time you have some ideal that contains it, that ideal is either just I itself or it was the entire ring, right? So it means that you can't stick another proper ideal in between I and the entire ring. So first we're going to prove that in any principal ideal domain, the idea of being a prime ideal is equivalent to being a maximal ideal. Now, a couple of videos ago when we talked about, when we first started talking about ideals, we already proved that in a ring with unity, any maximal ideal is prime, right? So we've shown that maximal implies prime when we're working in a commutative ring with unity, but here we're working in a domain, and so a domain is a type of commutative ring with unity. So that's certainly true. So what's left to prove is that we need to show that prime implies maximal. So need to show that prime implies maximal. Okay, and so if prime implies, so let's start off with a prime ideal. So let's let I inside our domain, we'll call our domain D, be maximal, be prime. And let's suppose that I is contained inside another ring J. Okay. And so what this means is that we are in a PID, and so each of these ideas are principal. So there exists an A in the ring such that I is equal to the ideal generated by A, and there exists a B such that J is the ideal generated by B. Now, I being contained in J implies that A is contained in J, which is the ideal generated by B, which implies that there exists some, let's call it C, such that A is equal to B times C. Well, since A is equal to B times C, that means that B times C is inside this prime ideal. So it's inside the ideal generated by A. And so this means that either B was inside A to begin with, which would complete the proof, or on the other hand, if B is not an element of A, this means that C is an element of A. So this means that C is inside A, and so then there exists some D, such that A times D equals C. And so then what we're left with is that A is equal to B times C, but C is equal to A times D. And so we can rearrange this to be A is equal to ABD. And then since we're in a domain, we're allowed to do cancellation. And so I can cancel the A's off and get that 1 is equal to BD, so B is a unit. And that means that if B is a unit, then the ideal generated by B equals the entire ring. Okay? And so going back through, this means that if I is contained inside of J, well, either B was inside of the ideal generated by A to begin with, in which case I and J would be equal. Or on the other hand, if B is not inside the ideal generated by A, then B had to be a unit. And so that establishes the proof. That shows that I was maximal. Okay, so now we're going to talk about irreducible elements. And so we can't talk about prime elements in quite the same way as we do in the integers. And so rather than that, we talk about irreducible elements. And so what it means to be irreducible, so we say that A is irreducible if whenever we write A as a product of two other elements of the domain, one of those had to be a unit to begin with. Okay, so A is irreducible if A equals BC implies that one of B or C is a unit, at least one of B or C is a unit, right? So in particular, this means that all units are irreducible because anytime you write a unit as a product of two things, both of those things had to be a unit. But there's going to be more things in general that are irreducible than that. So specifically in a polynomial ring, we need to be clear on what exactly the units are. So let's just recall that in a polynomial ring, the units are the constant non-zero terms. So these are all the degree 0 elements. And so one of the things we can say immediately from this point is that if the degree of f of x is less than or equal to 1, and f of x is non-zero, then f of x is irreducible. And so this just follows from, if you write f of x equal to the product of two things, g of x times h of x, well, the left-hand side has degree 1, and the right-hand side is equal to the degree of g plus the degree of h. And neither of these can be the zero polynomials, and so the only possible way to get these two degrees adding up to 1 is if over here this side is equal to 1 plus 0, and so that 0 there, that means that one of these had to have been a unit. So this is your corresponds to a unit. Okay, so every linear or constant polynomial that's non-zero is going to be an irreducible polynomial. Okay, there's one last sort of lemma-ish result that we need before we jump into the big statement of unique factorization. And that's if we have two different irreducible polynomials in the same ideal, then one of them, or then they differ by a unit. So you can write one as the other one times a unit. Okay. So one of the immediate implications of this is that the degrees of these have to match, because multiplying by a unit, multiplying by a constant in the field is not going to change the degree. Okay, and so to help us with this, I'm going to recall a corollary that we did in the last video, and that's that this is what we proved along when we proved that these polynomial rings over fields are principal ideal domains, and that's that if I is a non-zero ideal in the polynomial ring, then it's generated by any of its non-zero polynomials with minimal degree in the ideal. So you take any non-zero polynomial with minimal degree, then it's going to be generate the entire ideal. So if P of x and Q of x are both elements of I, and we're in a principal ideal domain, and so we can write I as being equal to the ideal generated by some other polynomial, g of x, for some g of x and f of x. Well, then that means that P of x had to equal g of x times something. So let's call it g of x times s of x. But P of x is irreducible, and so that means that one of these two, g of x or s of x, has to be a unit. It can't be g of x, because if g of x was a unit, then this would not be a proper ideal. So the fact that this is a proper ideal implies that s of x is a unit, i.e. it's one of the elements of the field. Similarly, with q of x, we can write it as g of x equal to t of x. That's what it means to be in the ideal. But then t of x has to be a unit. Because q of x is irreducible. And so then we can write p of x is equal to g of x, well, let's see, g of x, s of x, but g of x, we can write, since t is a unit, we can do t inverse to the other side. And so we have p of x is equal to t inverse. Really, we should drop the of x's of t and s, because they're just constants, times q of x. And so t and s are units, so t inverse times s, this is a unit as well. And so that gets us this fact. So the next step is to show that maximal ideals are generated by irreducible elements and vice versa. Okay, and so the ideal generated by p of x is maximal if and only if p of x is irreducible. And so we're going to prove this sort of in both directions at the same time, using the contrapositive. Right? So what's the opposite of p of x being irreducible? That means that p of x is reducible. So we have that p of x is reducible. So reducible, that means not irreducible. And so what does it mean to be reducible? What does it mean not to be irreducible? That means that there exists some g of x and h of x, which are not units, non-units, such that p of x is equal to g of x, h of x. Okay, and then this happens if and only if the ideal generated by p of x is a proper subset of the ideal generated by g of x for some g of x that's non-unit, that's not a unit. And you can't have equality here because the h of x that we had here is not a unit, so it has to have degree at least 1. So the degree of p here has to be strictly greater than the degree of g. And that's coming from the fact that the degree of p over here is equal to the degree of g plus the degree of h from the multiplication. Okay. And so then if p is contained in some other proper ideal, that's the same as saying that p of x is not maximal. So p of x being reducible or p of x being not reducible, this is equivalent all the way across to p of x being not maximal. And so then taking the contrapositive of this is saying that p of x being maximal is equivalent to p of x being irreducible. And then since maximal ideals are the same as prime ideals, we can just replace maximal with prime in the statement, and it still holds true. Right? So this means that in polynomial rings, being a p of the ideal generated by p of x being prime is equivalent to p of x being irreducible. Irreducible polynomials generate prime ideals, which are maximal ideals. Maximal ideals / prime ideals, these are the ideals generated by irreducible polynomials. Now we can get to the big statement. The statement that takes a whole slide to say. So, unique factorization in polynomial rings. So for any f of x in the polynomial ring over f, there exists irreducible polynomials p1 through pk such that we can write f of x as the product of p1 through pk. And so this is the existence statement. Existence ends with has a c near the end. And so you can factor any polynomial into irreducible polynomials. And then the second part is the uniqueness part of this. Although the uniqueness in this is going to look a little bit weird because it's unique up to multiplication by a unit. And so what the uniqueness statement is that any time that you do this factorization twice, so you start off with f of x, and you have f of x is equal to the product of p1 through pk, and then you start over again, you get some other factorization, and you say that f of x is equal to q1 through ql, then it has to be that there's the same number of irreducible polynomials on each side. And so that's k is equal to l. This is counting the number of irreducible polynomials on each side. And for anything on the left, there has to be something on the right such that they differ by at most by a unit. And so what we mean by that is that for each pi of x on the left, then there is some qj of x on the right such that pi of x is equal to a unit times qj of x. Okay, so this all here, this is the quote-unquote uniqueness. Okay, so there's two things to prove. So first, let's prove the existence. Okay, and so we're going to do this. We're going to do this by induction on the degree of f. So by induction on the degree of f of x. And so we already did the base case. So the base case is we already showed that degree 0 and 1 polynomials are irreducible. And so that's our base case. So then for our induction step, so let's assume that for some n, for any polynomial, let's call it g of x, with degree of g of x being less than n, we have that g of x can be factored into irreducibles. Okay, so now let's let f of x have degree n. So if f of x is irreducible, then we're done. Right? It's already factored into irreducible polynomials. It's just itself. So on the other hand, if f of x is equal to g of x times h of x, and neither of these are units, so they're at least degree 1. So with degree of g of x, comma degree of h of x greater than or equal to 1, well then, by the induction hypothesis, we can factor g and h, because they have smaller degree. Because their degree has to be, if both of their degrees are at least 1, and their product gives us the degree of f, then they had to have smaller degree than f. And so we can factor g and h, and f of x equals the product of this factorization. So we have g written as a product of irreducible polynomials, h written as a product of irreducible polynomials. Multiply those together, that gives us f as a product of irreducible polynomials. So that tells us that we can factor anything. Now we have to prove the uniqueness. And again, we're going to do this by induction. And so remember, for uniqueness, we're supposing that f of x equals p1 of x times pk of x, where all of these are irreducible, and also equal to q1 of x ql of x. Okay, and so we're going to do this by induction on K. And so our base case is that if f of x equals p1 of x equals q1 of x dot 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 ql of x, well then if p1 is a unit, so if p1 of x is actually just in f times 0, then that means that each qi is in there as well. None of them could have degree bigger than 0, otherwise the degree of the right-hand side would be bigger than the degree of the left-hand side. And so you just have that all the p's and q's are units. And so there's nothing really to show there. Otherwise, let's suppose, without loss of generality, let's suppose that q1 of x is not a unit, because if overall f of x is not a unit, then at least one of the polynomials on the right-hand side has to not be a unit. Otherwise, there's no possible way to get the degree bigger than 0. So this is without loss of generality. We're saying that q1 of x is not a unit. And so then we have that p1 of x is equal to q1 of x times q2 up to the rest of them. Well, since p1 of x is irreducible and q1 of x is not a unit, that means that all of these had to be units to begin with. And so really, what we really had was that p1 of x is equal to a unit times q1 of x. Okay, and so one irreducible polynomial on the left, one irreducible polynomial on the right, that establishes the base case. Okay, so now I'm going to clear this off to do the induction step. Okay, so now we're up to the induction step. So for the induction step, we're going to assume that it's true for k minus 1. So if there is only k minus 1 polynomials left on the left-hand side. Polys on the left-hand side. Okay, and so since p sub k, this is an irreducible polynomial. Irreducible polynomial. And so this implies that the ideal generated by p sub k is prime. And then we notice that when we have something times p sub k, and so this has to be, and this whole thing is f of x. So f of x is an element in the ideal generated by p sub k of x. And so that means that the product of q sub 1 of x up to q sub L of x is inside p sub k of x. Okay, so now this is the real big step right here. So we have this product of all of this q1 through ql is inside a prime ideal p sub k of x. So remember that prime ideal means that anytime you have a product, then one of the things being multiplied together has to have been in the ideal to begin with. Okay, and so when you have it, it's written just for 2, but really it follows for any number of things you have multiplied together, right? So if you have, the way to think about it is like this. This means that either q sub 1 is in p sub k of x, or the product of everything else is in there. In which case we've kicked out q sub 1 of x. And so we can just repeat this process. So we just repeat until we find somewhere down the way we get that q sub j of x has to be inside p sub k of x. Okay, and so if q sub j of x is inside p sub k of x, well, this means that p sub k of x and q sub j of x, these are 2 irreducible polynomials, both inside the ideal generated by pk of x. And so by what we saw before, this implies that p sub k of x is equal to some unit, call it a sub j, times q sub j of x, where a sub j is a unit. And so this is what we proved a little bit ago. Okay, so now we have that p sub k of x is equal to a unit times q sub j of x. Let's clear out some space again. So p sub k of x is equal to a unit times q sub j of x. And so then this means that p sub 1 of x up to p sub k of x, we can rewrite this as a sub j of x times p sub 1 of x up to p sub k minus 1 of x times q sub j of x. And then this is still equal to what we had on the right side to begin with. So q sub 1 of x, q sub L of x. And inside this list here somewhere, there is q sub j of x. Now so now we have q sub j of x on both sides of this product. And a sub j is just a unit. It doesn't need any of x there. Let's point out that this is just a unit. Mainly I'm writing that there just to remind myself so I don't write it like as if it's a bigger polynomial. So the fact that we're in a domain and we have the q sub j on both sides, the fact that we're in a domain means that we can cancel these off. We're allowed to do cancellation. And so then we have that a sub j, p sub 1 of x, p sub k minus 1 of x is equal to q sub 1 of x to q sub j minus 1 of x. We took out q sub j, so it's gone. So we have the indexes beneath it and below it up to q sub L. And in fact, we can move the a j to the minus 1 to the other side. Okay, and so now we're down to, we've gotten rid of one of the polynomials on the left-hand side, and so now we can apply the induction hypothesis. And so really we have k minus 1 irreducible polynomials on the left-hand side, L minus 1 irreducible polynomials on the right-hand side, but by applying the induction hypothesis, that means really that k minus 1 is equal to L minus 1, and so then that gets us what we want. So that finishes the proof. And that's it. We're done. So what this means, the big takeaway, is that in f of x, we can factor polynomials uniquely and this uniquely is up to units, so up to elements in the field, similar, so as in how we factor integers. These are both polynomials over a field, and the integers, these are both examples of unique factorization domains. And so there's a lot of the same ideals. There's similar things running between them. Okay. That is all for this video. I will see you again soon.